In the space below, I'm going to draw electric field vectors. We'll assume that each object has an equal magnitude or size of charge. But here we have a positive charge on the left and a negative charge on the right. We're going to also assume that these charges are far enough apart so that they don't interact substantially with each other. And I want to show the difference between drawing vectors and drawing field lines. So in order to draw vectors, we want straight arrows. And we can pick any point of our choice, because here we're not drawing the force that two particles feel between them. We're drawing what the force would be if there was another particle in the field to feel that force. Similar to the way that we can draw gravitational field vectors in the space around a mass, we can draw electric field vectors in the space around a charge. Conventionally, we'll imagine a positive test charge when drawing the field. So let's pick just, let's say 8 points around this particle. And which way would a positive charge be pushed if it was in those locations? Well, we know that positives repel positives. So the field will point away from the positive charge. And that's what we want to draw, is just the electric force that would be at these points if there was a positive test charge there to feel it. This is a drawing of the electric field. Now we can also pick some other points. Let's try some points that are farther away. And what would the strength of the push be like out there? If you take two sticky tapes of the same type of charge, like say 2 top tapes, which are positively charged, and bring them close together, the closer they are, the stronger that repulsion between them becomes. And if you bring them farther apart, you might not notice much of a repulsive force at all. And so that's what happens with the electric field, is it's going to be weaker the farther you are away from the charge. And we want to indicate that with just smaller vector arrows. All right, that's a good drawing of the electric field around a positive charge. Now let's do the same for a negative charge. Once again, we'll pick some arbitrary points around our charge. But we want to show what the direction of the force on a positive test charge would be. Well, just imagine that there was a little positive charge there. Which way would it be pulled? Would it be pulled toward the negative or away from it? The answer is it would be pulled toward it. So the directions of our vectors have to reflect that. All right, and then we'll just draw what the field would be like farther away from the charge. It'll be weaker, but it'll still pull in. There we go. That's the electric field. We also want to utilize a different graphical method of showing the electric field, and that is electric field lines. Electric field lines are nothing more than just connecting the electric field vectors into smooth, continuous lines. And we want to put arrows showing the direction. So around a positive charge, the field points away from the positive charge. So we just want to show that with some simple arrows. It's a similar approach to the above, but just a little different. For a negative charge, the lines will look the same, except their direction will be switched. Field lines point in toward a negative charge. All right. What if we have two particles that are near each other? What would the field lines look like now? Well, we just want to take the two drawings above here and connect them. So we need a smooth continuous line that goes from the positive all the way to the negative. We're going to see that our lines will bend, and lines that leave the positive will have to come back and enter the negative. We want our arrows to show the direction of the field. And even though we're going to go off the page here, it's assumed that the field lines do keep going, and they will arc all the way around to come back, and they'll come back and settle on the negative. This particular field line, though, points directly to the left. And we want to have an equal number of field lines leaving the positive as come in toward the negative. So we'll have this situation. There we go. Count them up. 1, 2, 3, 4, 5, 6, 7, 8 field lines leaving a positive. And 1, 2, 3, 4, 5, 6, 7, 8 field lines coming in toward the negative. This is common when our charges are equal in magnitude. We'll see cases later where the charges are unequal, and we'll see how things will be a little different in that case. In that case, you can have more field lines leaving one object than come into the other, for example. Down here, notice that we've got two positive charges. So that's going to be a little different. In this case, we need field lines to leave both of them, and they won't come back into these particles. Some easy ones to do would be just, let's have a line leave this guy and not come back. We'll do the same thing over here. And we could have a situation where a line leaves this particle, but it is also repelled by the other particle. So it might look like this. Okay. If a field line leaves this guy and goes to the left, it's repelled by the other positive. And so we'll actually see something like this. It'll want to just form sort of an asymptote here where they go up toward infinity. Field lines can never cross, so they have to stay separated here. That's a good drawing. So let's see, we've got 1, 2, 3, 4, 5, 6 field lines leaving this particle. and 6 leaving this particle, so it's nice and symmetrical.